Okay, so it is my pleasure to introduce Quentin Berger. So Quentin had his PhD at ENS Lyon under Fabio Toninelli. He spent some time in Rome at the University of Roma Tre during his PhD. Then he was an assistant professor at the University of Southern California in the US for 2 years. And afterwards, he has become a maître de conférence in Sorbonne Université here in Paris. And more recently, he has also become a maître de conférence HDR. So the title of his talk today will be Directed Polymers and the Stochastic Heat Equation with EV-tail noise. So please, Quentin, the stand is yours.
Okay, well, thank you, Matteo, for the introduction. Okay, so yeah, as I said to the organizers, I'm a mathematician, but I'll try to go as slow as possible on the mathematical side. And if you have any questions on the physical side, please feel free to interrupt or slow me down. Okay, so I'm going to talk about some work I did with Carsten Chong and Hubert Lacoin. Actually, I started with Hubert Lacoin working on directed polymers. Okay, so it's a model from mathematical physics, and at an online seminar, just as this one, there was Carsten in the chat, and he was asking us a lot of questions. He was a specialist of the stochastic heat equation with Lévy noise, so we ended up working together. Okay, so I'm going to present well, the latest works. So there are 2 parts of the works. The first part is with Hubert Lacoin, which is more focused on directed polymers, and maybe I'll spend more time on that side. And there's another side of the work, which is more on the continuum part, which is the stochastic heat equation. Okay, so what is the stochastic heat equation? So the stochastic heat equation is that equation. So you have a field on time and space. So space is RD, and you want to construct or study solution of this type of equation. Okay, so if you don't have the second part, it's just the heat equation, but here you add a multiplicative noise. Okay, and can model a particle in a field of inhomogeneous field. Okay, and so here is a space-time white noise, and people have been looking at the case of Gaussian space-time white noise. And here in the problem we're interested in, we're looking at some a larger class of noise, and maybe noise with atoms and jumps. Okay, so what do I mean by a solution of this equation? Well, it's the integrated sense, also called the mild sense. So I denote rho Tx the heat kernel. Okay, so it's the solution of the heat equation without the noise. And we say that a function u, or field u, satisfies the stochastic heat equation if it verifies the integrated version of the first equation that I wrote above. Okay, so here what you have is that u is the integral of the heat kernel against the initial condition, and then you integrate u against the heat kernel with the Lévy, with the noise at position s and okay, so u sy then collects a noise at site s y, and then there's the heat kernel. Okay, so that's what you want to produce and give sense to this kind of solutions. And what you could do is, okay, if you take, for instance, u0 equals 1, okay, so you start with a flat initial condition, and you iterate the equation above. Okay, so the first term will give you just 1, because you integrate the heat kernel over space, so it gives you 1. And then you have this integral of the solution you have times the heat kernel. And you can plug in again the fact that this solution is 1 plus beta and the integral, etc., and you iterate that. And in the end, what you have is some kind of iterated expansion of the solution of the stochastic heat equation. Okay, so that's a way to say, well, this expansion is a solution of the stochastic heat equation. Okay, so one of the problems is to make sense of this expression. Okay, if you have a Gaussian white noise, well, you can make use of theories of Wiener-Chaos expansion of Gaussian white noise, and okay, so all the terms in the sums are orthogonal in L2, and so you can do some L2 calculations and compute the norms of all the things and show that it's absolutely convergent, so you can make sense of this infinite sum. But in the case where the noise, for instance, does not have a finite second moment, well, you're a bit stuck and you need to find some other ways to define that. Okay, so that's an overview of what we want to do is actually make sense of this last part. Okay, and we will call that a solution to the stochastic heat equation. Okay, so this is the goal, but actually what I will start with in this talk is introducing the directed polymer model, which you can see as a discrete version of the stochastic heat equation. Okay, so a way to make sense of ill-defined or just partial differential equation is stochastic partial differential equation is to somehow find an approximation of the equation and construct solution of the approximated equation and make the approximation go to 0. And so if you have something that converges, you can hope to say, well, this will be the limit will be the solution of the equation. Okay, so the directed polymer model is, in a sense, doing that by discretizing time and space. Okay, but it's also a model of interest on its own. Okay, so what is the directed polymer model? Okay, so the directed polymer model, it has been introduced in the 80s by two physicists, and in the beginning, it was introduced to study the interface in Ising models. Okay, so the interface between a phase of plus and a phase of minus. And to simplify, they say, okay, well, let's assume that this interface is directed, so you don't have some kind of loops going backwards. So it simplifies the analysis, and you can see this interface as a directed random walk. Okay, so you take SI, a simple random walk on ZD. Okay, so you have one direction which is time and which is deterministic, and one direction which is space, which is random, and that gives you the trajectory of a polymer. Okay, so this is the shape of your polymer. It's given by the trajectory of a simple random walk. As I said before, you can imagine that it's also the shape of an interface between a phase of plus and a phase of minus. And what you do is you place this polymer inside a field of random variables that model inhomogeneities. Okay, so you can think about putting a polymer in a solvent which has impurities, or putting some random interactions in the Ising model. And so you place a random environment, so IIT random variables everywhere, okay, in space and time. Okay, so you call that a random environment. So it's a directed polymer placed in a random environment. Okay, I've called the random variables eta. And so they are IIT. Okay, so you can think about that as the random environment being completely renewed each unit of time. Okay, it's the analogous of the space-time white noise I alluded in the previous slide. Okay, so how do you construct the model in that case? So the idea is for each trajectory of the random walk, okay, so for each shape of the polymer, you look at the random variable that sit on the trajectory, and it gives you a weight of a trajectory. Okay, so for each trajectory, you have a weight which is given by the product of 1 plus beta times the random variables that you see along the trajectory.
Sorry, Quentin.
Yeah.
Maybe it's a trivial question. It's just I didn't understand. What do you represent in this graph? Because I don't, because you have a random walk in Z to the power D.
Yes.
And what's the curve that you are?
Okay, so the curve you place. Okay, so it's what is called the directed random walk. So at each step you take one step to the right and one step up or down. Okay, imagine D equals 1.
Yes. Okay.
Okay, so at each step you go right and up or down.
Mm-hmm.
Okay, so the idea is that you can think about that as you draw the trajectory of a particle. Okay, so you have a particle going to the right. Okay, so it's the first coordinate, you can think about that as time. Okay, so time passes and you record where the particle is. Okay, and that gives you the trajectory of a particle, and or you can think about that as the shape of your polymer. Okay, so the dots, you can think about them as the different monomers of the polymer. And so the next monomer is either up or down compared to the previous one.
Okay.
Okay, so you have a monomer, a polymer, sorry.
So every in any case, every step you move right.
Yes,
step.
exactly.
And then
okay.
either up, either down.
Yes, exactly. So you have one deterministic direction. It's time. We can think about that as time. And the transverse direction is space. Okay, so the time every time goes up by 1, but in space you fluctuate.
Okay. Okay. Thank you.
Okay, so yeah, you have two sources of randomness. You have the first is the randomness of the random walk trajectory, okay, of the shape of the polymer, and the second randomness is from the environment. Okay, so the environment you can, okay, as I said before, it can be thought as impurities. Okay, you have impurities everywhere in your medium, and you place the polymer inside that medium, and what you'll see is that it will have some interaction. Okay, so you could think about giving some energy to each configuration of the polymer. And okay, here I don't represent it in the exponential form as usual for Gibbs measure, but I present it in a product form. It was actually the original formulation from Hughes and Henley in this model. Okay, so what you have now is you fix your environment. Okay, you fix the colors of the random variables that you put everywhere. It's called the quenched disorder. Okay, so that's something that is fixed and you don't touch that. And you consider a new measure on trajectories of the polymer. Okay, so a new measure on configurations of polymers by saying that that new measure gives a mass which is proportional to the product of 1 plus beta times the random variables that you see along the trajectory. Okay, so what does this measure do? Sorry, what does this measure do? It gives a larger weight to trajectories that visit large values of eta. Okay, so you favor trajectories visiting regions in the environments of where the eta is large. Okay, is that clear?
Yes, does that make sense? Yes. Thank you.
Okay. And okay, yeah, so it's important to understand the model, and because I will talk about properties of this. So what you want to know is, okay, so you want to study that measure, this new measure, which I will call a polymer measure, for a typical realization of eta. So for typical environments, when the length of the polymer N is very big. Okay, and beta is a parameter that tunes the coupling between the polymer and its environment. Okay, so if you take beta equals 0 here, all trajectories will have the same weight. So it's the uniform measure on all trajectories. Okay, so you want to understand this kind of properties. Okay, so here I want the weight to be non-negative. So what I will assume that eta is always larger than -1. The weight is always non-negative, and I will assume that the eta are centered. Okay, just otherwise it's just you can factor the expectation out, and okay, it doesn't change much the polymer measure. Okay, it's just a technical assumption. Okay, so that's the measure you want to study. And okay, so there are questions. Do the trajectories actually look like simple random walk as usual? So it doesn't feel the impact, the effect of the environment? Or does it look like something different and has some kind of localization properties? Okay, so that's the question. The question is, I wrote again the measure I want to study. I want to understand the shape of trajectories drawn with respect to that measure. Okay, and the z here, it's the partition function. It normalizes the measure to a probability measure. Okay, so what you can do is express exactly what the partition function is. Okay, so the partition function, what it is, it normalizes everything to a probability measure. So what you have to do is you have to sum over all trajectories of the simple random walk of the Gibbs weight. Okay, another way of writing that is to write that it's the expectation with respect to the simple random walk, not with respect to the environment, of the weight of the trajectory S. Okay, so this is a random variable in eta. It depends on the random environment, but it does not depend on the trajectory, because in that expectation you have summed over all trajectories. And you can also consider what is called the point-to-point partition function when you restrict trajectories to end at position X. Okay, so in the first case, trajectories can end up anywhere. And in the second case, the trajectories have to end up at site X. Okay, so it's point to point. And okay, so you see that if you want to compute the probability that under the polymer measure that the random walk ends at X, that the polymer ends at X, what you have is just the ratio of these two partition functions. Okay, so what I'm saying is that actually what you need to do is focus on the partition functions, either the point-to-point partition function or the partition function. So from now on, I will not talk much about the measure in itself, but more about the partition functions, since you can extract a lot of information from them. Okay. And okay, so as I said before, I'm looking at the product weight instead of some exponential weight. In the literature, you will find also, if you look at this model, the exponential weight with an energy which is the sum of the random variables you see along the trajectory. And okay, it's just a transformation to go from one model to the other. Okay, just have to define eta as this function of omega, and you'll find exactly the same model. Okay, so just the difference is that the transformation depends on beta. Okay, so if you want to study the dependence on beta of the model, the dependence on beta will not be exactly the same in the two models. And the reason why I look at this product form is because of its relation to the stochastic heat equation. Okay, so let me explain to you what is the connection with the stochastic heat equation. I said in the introduction that it could be considered as a discrete version of the stochastic heat equation. And here is how. Okay, so look at the partition function
May I ask something?
Yes.
Beta corresponds to 1 over temperature, or?
Yeah, here beta corresponds to 1 over temperature in the exponential form. And yeah, in the product form, it's a bit more complicated, but it's roughly that. It's roughly related to the inverse temperature. Yeah, it's. I know that the conventions between physicists and mathematicians are different, and the mathematicians, they don't like to have a minus here, and so they just put a plus and they reverse omega into minus omega, but that's no difference. Okay, and okay, so here I'll take the convention of the product form with beta, yeah, the inverse temperature. Okay, so here what you want to look at is how does these partition functions evolve as a function of n. Okay, so the length of the polymer, and as I said before, n, you can think about that as time. Okay, so I just rewrote the point-to-point partition function, except you go up to a length n+1. Okay, so this is the Gibbs weight of a trajectory. You restrict trajectories to end up at x at time n+1, and you sum over all such trajectories. Okay, so here what you can do is use some kind of Markov property. You say, well, here in that product, since the last one is as n+1 equals x, what I have is I have 1 plus beta and the random variables at time n+1 and position x. And then you can sum over all previous positions. Okay, so I have 1 over 2d because I can come from any of the neighbors of x. And I sum over all the y's that are neighbors of x. And here I transform, okay, I just sum over possible positions of the random walk at position y at time n. Okay, and here you see that I have reconstructed the partition function, the point-to-point partition function from at time n up to point x. Okay, and I have this 1 plus beta that I will separate into 2 parts. Okay, so I have first the 1 over 2d, the partition function point-to-point ending up at position y at time n, and then I have beta times the random variable times this quantity. Okay, and this you can think about that as a discrete analog of the stochastic heat equation. Okay, so if you subtract, if you look at zn+1 minus zn, okay, so you can think about that as the discrete time derivative. What you have is this quantity, this first sum minus zn, which is the discrete Laplacian, plus, okay, so here there's a typo, it should be n+1 inside of n here, but plus beta times a random variable times some kind of averaged partition function, point-to-point partition function. Okay, so it looks a lot like the stochastic heat equation. We have that the derivative of time is the Laplacian plus beta times a noise times u. Okay, so that's the connection, and that's why it's interesting to put the product form in the Gibbs weight, because when you have the product form, you have this 1 plus, which separates very cleanly into 2 parts, the Laplacian part and the noise part. Okay, so here the noise is clearly multiplied with the average Laplacian. Okay, so that's one of the reasons why this model has been gaining interest in the past years, because of the connection to the stochastic heat equation. Okay, are there some questions here? No? Okay, so yeah, I'll come back to this connection later. Okay, so let me come back to the directed polymer. I will just review some some results that people have had on this model, and the main result is to find the occurrence of the phase transition. Okay, so if you look at this partition function, you can see, okay, so if you're a mathematician, you show that it's a non-negative martingale. Okay, so if you're not a mathematician and you're not used to martingales, just, okay, it's a sequence of random variables, and you can show that this sequence converges almost surely to some limit. Okay, so that's the result of working with martingales. Okay, and you can see actually a phase transition in the limit that you obtain. Okay, so there's a critical beta. Okay, so critical temperature, if you wish. Okay, and okay, so beta small implies that the limit that you obtain is non-degenerate, and beta large implies that the limit that you obtain is degenerate. So the limit is 0. And in the first case, you can show that you have some kind of weak disorder phase, meaning that the trajectories under the polymer measure look a lot like simple random walks. Okay, so these are results. I won't go into the details, but there are lots of results you can show. But okay, mainly you can show that the trajectories have the same scaling as the random walks. So if you divide them by square root of n, you will obtain a random motion. And if beta is large enough, then you have what is called strong disorder, in a sense that you can make precise, and I won't make it precise here because I would have to write too many details, but the idea is that you kind of have some favorite regions in the environment where the polymer goes. Okay, so you have some kind of localization properties of the polymer. Okay, and okay, so this is a phase transition. Okay, you see that if beta is small, you have one type of behavior, and if beta is large, you have another type of behavior. And you can also see that if you look at the free energy. Okay, for the free energy, okay, so the free energy is 1/n log of the partition function. You take the limit, which is a quantity which you can show is non-random, and also called the pressure. And you can also show that it has some phase transition. Okay, and okay, so one open problem in this model is to show that the phase transition occurs at the same critical temperature, the same critical beta. Okay, and this has been open for 30 years, and I don't think people are close to proving that. But okay, everyone believes it. Okay, so since I said I would focus on the partition function, I will stick with the first definition of the phase transition. The question that remains to show is, okay, here I did not exclude the fact that beta critical is equal to 0. So it could be that the first case never occurs. Okay, meaning that as soon as beta is strictly positive, you have strong disorder. And so this is the first result I want to say. Okay, so this depends actually on the disorder that you're looking at. Okay, so remember you have your field of IID random variables. If these random variables have a finite second moment, then you can show that in dimension d equals 1 and 2, the critical point is equal to 0. Okay, so it means that as soon as beta is strictly positive, you have strong disorder. So you can think about that as having no phase transition and being always in the strong disorder phase. On the other hand, in dimension d larger than 3, the beta critical is strictly positive. Okay, so you do have a phase transition. And this is done, it's actually not that difficult to prove these two results. This is done by second moment computations, let's say. Okay, in the second case, when the environment does not have finite second moment, what you need to do is to assume a little bit more on the environment. Okay, so you assume that it has heavy tails. Okay, so that the random variable takes a value larger than t with a probability that decays like a power of t, okay, with that power between 1 and 2. Okay, so it means that you have more easily large values of eta in your environment. So you could think about it as helping to have localization. Okay, so disorder should be, okay, so the strong disorder phase should be larger. It should be easier for disorder to be strong. And this is indeed what proved Roberto Viveros. It proved that you kind of have the same criterion as before. If the dimension is small enough depends on the tail of the probability distribution of eta. Then you don't have any phase transition and you always have strong disorder. And if dimension is large enough, then you have a phase transition and you have a transition between weak disorder and strong disorder. Okay, so if you notice, if you take alpha equals 2, you recover the fact that if the dimension is 1 or 2, then the beta critical is equal to 0. And when alpha goes to 1, you have a critical dimension, and the critical dimension goes to infinity. Okay, so the smaller the alpha, the heavier the tail, the easier it is to be in the strong disorder phase. Okay, so that was an overview of the results that you could show. And as I mentioned before, it's in the weak disorder phase, you have the same properties as the simple random walk, and the strong disorder phase, you have some localization properties that you don't have for the simple random walk. Okay, so that was an overview, and now what I want to say is I want to make the bridge between the directed polymer model and the stochastic heat equation, and this has been done over the past decade by many people, and I will give some of the results. And as for the directed polymer model, there will be two cases. Either you have a finite second moment, this will be some kind of Gaussian case, or you don't. And this will be the Lévy case. Okay, so what is the idea? The idea is that in the case where the beta critical I introduced before was 0, meaning that you don't have a phase transition, meaning that you are always in the strong disorder phase, maybe the right idea is that it's not that you don't have a phase transition, it's just that you're not looking at the correct scale to see the phase transition. Okay, so the idea is to zoom in around beta equals 0 to see the weak to strong disorder phase transition. Okay, so what you do is you take beta as a function of the length of the polymer, and you take that inverse temperature, go to 0 at the correct speed. Okay, you can think about that as having a very, very long polymer. So n is fixed, very, very large. And you want to find the correct scaling for beta, where you see a transition between weak disorder and strong disorder phase. Okay, so you want to see when the disorder starts having an effect on the model. Okay, you can see that in another way, saying that if beta n goes to 0 too fast, for instance, if you take beta equals 0, if you take beta equals 0, the partition function equals 1. Okay, so if you take beta and go to 0 very, very fast, you will always have that the partition function converges to 1. And if beta n goes to 0 too slowly, then, for instance, if you take beta strictly positive, then you have that the limit of the partition function is equal to 0. Okay, so finding the correct scale would mean that you find beta n that goes to 0, such that this sequence of random variable converges to some non-trivial random variable, which is neither 0, neither 1. Okay, and if you manage to do that, you'll be actually in the correct scaling to construct solutions of the stochastic heat equation. Okay, maybe I'll show you afterwards the results. Okay, so the idea is, repeating myself, but the idea is that you find the correct scaling at which somehow disorder kicks in. Okay, it's the exact scaling where you have still diffuses trajectories as for the simple random walk, but you feel the influence of the disorder. Okay, so this is what has been done by some people, and the first set of results was by Albers, Hadin, and Questel. Was published in 2014 in dimension d equals 1, and in the case of a finite second moment. Okay, so in the case of a finite second moment, what you can look at is if you take beta n to be n to the minus 1/4. Okay, okay, maybe I'll skip explaining where this exponent comes from, but okay, if you want, I can show you where this exponent comes from. If you choose exactly that scaling with another parameter beta hat, then the partition function, okay, converges to a continuous partition function. Okay, and this continuous partition function, I can give you an expression. The expression is the analogous in the continuous world of the directed polymer partition function. Okay, so directed polymer model, you had a random walk. Here in the limit, you'll have a Brownian motion. And in the discrete directed polymer model, you had IID random variables with finite second moments. So in the limit, you'll have 1 + 1 dimensional Gaussian white noise. Okay, so it's the scaling limit of the field of random variables. Okay, so here I put some quote marks because, okay, so the continuous partition function is the average with respect to the Brownian motion of the exponential of, okay, you have this parameter beta hat that remains, times this means that it's the white noise that you see along a Brownian trajectory. Okay, and it does not make sense as such because to see something non-zero, you need to integrate the white noise on something which has a non-zero volume. So you cannot make sense of that directly, but what you can do is you expand the exponential. Okay, so it's a Wick exponential. You expand the Wick exponential, and you exchange the sum with the average with respect to Brownian motion, and what you'll see appear is exactly the kind of expansion I showed you on the first slide, saying, okay, so you get 1 plus sum of the beta k, and you sum over the times and space points, and you have the product of the heat kernel between these space-time points, and you collect the white noise at these space-time points. Okay, so that's the formal expression of what I've put between the quote marks.
Sorry, Quentin, I have a question. Yeah. So it is
Yeah.
about the use of the columns. So do the column mean like a normal order?
Yeah, it's the Wick product. It's
okay.
Yeah.
It's the Wick theorem. I mean, you are
exactly.
Then this gives the ordering on the times below.
Exactly. Yes.
I see. Thanks.
Okay, so here you see that that if you take the correct scaling, then the partition function converges to an object, to a continuum object, which solves the stochastic heat equation. Okay, here with the flat initial condition. Okay, so this was already an interesting result, and the thing is that people already studied before the stochastic heat equation with the flat initial condition and showed that this was the solution. This theorem tells more that, for instance, okay, so let me rephrase that, sorry. What this theorem was about was more to say that the discrete approximation given by the the directed polymer model converges to the continuum object that people have been studying. Okay, so here I think I didn't plan on giving you the results, but if you look at the stochastic heat equation in dimension d equals 2, people did not know how to construct a solution of the stochastic heat equation. Okay, it's ill-defined and people were not able to see how to construct things. And last year there were recent results by Francesco Caravena, Rongfeng Sun, and Nikos Zigouras, who showed that you can do somehow the same type of approximation, take a good scaling for the beta n, and show that the sequence of partition function converge to something non-trivial. And they say, well, this something should be understood as the solution of the stochastic heat equation in dimension d equals 2. Okay, so you can see the two faces of the same coin. Either you start from the stochastic heat equation and you say, I know how to study that, and I construct a sequence of discrete models that converge to that. Either you don't know how to construct solution of the stochastic heat equation, and you say, okay, well, I will construct a sequence of discrete models that converge, and I will say the limit should be the solution of the stochastic heat equation. Okay, so this is what people have been doing. So there are these two aspects of the problem. Okay, so let me give a very quick idea of the proof. I won't spend too much time. Okay, so here's the expression of the partition function. You can expand the product to 1 plus beta, and you get a big expansion. And here you recognize exactly the same expansion as I did in the continuum, but in the discrete world. Okay, so here you have the transition kernel for the random walk, and here you have the product of the random variables. So you show that each term converge, and to see where the beta n equals n to the minus 1/4 comes from, let's look at the first term, k equals 1, which is this one, and do a second moment calculation. Okay, if you do a second moment calculation, okay, I'm going a bit fast, but it's just a standard calculation. You'll see that the variance, okay, so it's centered, and the variance is beta n squared times, okay, so that's the mean number of intersections between two independent simple random walk, which is of order square root. Okay, so the variance is of order beta n squared times square root n. And this tells you that if you want the first term to converge, you want the variance to converge. So you want to take beta n to be n to the minus 1/4. Okay, so yeah, that was just a quick calculations. It's just to show that the n to the minus 1/4 is not mysterious. It just comes from a second moment calculation. Okay, so now I'm arriving to the first result I proved with Hubert Lacoin, was in the case where you don't have a finite second moment, so you have an infinite second moment, and recall the assumption I made before, that the tail of the random variable eta decays as a power t minus alpha, with alpha between 1 and 2. And recall also that in that case, the beta critical equals 0 corresponds to having dimension d smaller than 2 over alpha minus 1. Okay, so we're focusing on the case where beta critical equals 0, because the intermediate disorder scaling is only in that case. Okay, so you zoom in around 0. Okay, so what we've shown is that if you take beta n to be a power of n, okay, so n to a negative power, where I've written that power here, it's d over 2 alpha factor 1 plus 2 over d minus alpha. And notice that it's strictly positive if you take alpha strictly smaller than 1 plus 2 over d. Okay, so beta n goes to 0. Then in that scaling, the sequence of partition function converges also to a non-trivial random variable. Okay, and what is this non-trivial random variable? It's formally the same as before, except that you replace the Gaussian white noise by the equivalent, which is, the equivalent when you have this tail assumption, which is an alpha stable Lévy white noise. Okay, if you don't know what alpha stable Lévy white noise is, it's not really important. It's just that it's a noise which has big jumps in it. Okay, contrary to the Gaussian noise, it doesn't have a finite second moment, and it's somehow Poisson noise where you have peaks very high in the noise. Okay, so it's more difficult to make sense of this expression, and maybe I'll tell you a bit more about that. But another thing that we proved with Carsten Chong and Hubert Lacoin is that once you know how to define this expression, once you know that this is well defined, you can also prove that it solves the stochastic heat equation with that Lévy noise. Okay, and it's a bit more complicated because you have to somehow exchange limits. But okay, so here is more or less the same idea as I explained before. Here we start from a discrete model, and we show that it converges, and we show that the limit we obtain is the solution of the stochastic heat equation with some noise which has no finite second moment. Okay, so let me explain a bit more where the scaling comes from, where this exponent gamma comes from. Okay, so let me go back to the expansion I wrote before and look at the first term. Okay, so the first term is beta n times the sum of the simple random walk transition kernel times the random variable eta ix. And here I cannot do a second moment computation because the eta do not have a finite second moment. So instead, I have to do something a bit different. I have to make some series of approximation. Okay, what I'm saying is that first of all, this random walk kernel, it's of order n to the minus d/2. Okay, so this is the local limit theorem, as long as the x is smaller than square root of n. Okay, so if x is larger than square root of n, this probability will be exponentially small. So I will discard these terms. And somehow, more or less uniformly, for all x smaller than square root of n, the probability that a random walk ends exactly at x is of order n to the minus d/2. Okay, and then I need to know what this sum looks like. What is the order of this sum? Okay, so the idea is that you have a sum of heavy tail random variables, and you just have to know that for heavy tail random variables, so they are centered, the order of the sum is the same as the order of the max. Okay, and the order of the max, you can compute that fairly easily. Okay, so what you need to do is actually count how many variables there are and how many are there. So there are n times n to the d/2. Right. Okay, so that's the number of variables that you're looking at, and the order of the maximum of that many IID random variables with tail alpha is the number to the power 1/alpha. Okay, so that's standard probability calculation. Okay, it's a nice exercise. Okay, so here I have somehow the order of xn, and you see that what you find is that you have beta n times n to some power. So you need to take beta n to be n to the minus that power. And that power, I just rewrote that as d over 2 alpha, 2 over t plus 1 minus alpha. And it's positive. Okay, so that's just a by hand calculation of trying to find the correct order for the beta. Okay, so that's somehow summarizes the results we had with Hubert and Carsten Chong. Okay, so now I have a bit more than 5 minutes left. I will try to explain to you how do we make sense of that, because here I didn't tell you anything about how to make sense of that, which is actually an important part of that theorem. Okay, so I will go back to the continuous model. And okay, so the stochastic heat equation with Lévy. Okay, so I will focus on the continuum partial function. Okay, so we want to make sense of this kind of thing. How do we do that? As I said before, you cannot do L2 calculations to show that all the terms are bounded in L2, and okay, so the L2 norms are summable, things like that. So what we did was to say we will use an approximation of the noise. Okay, instead of looking at that quantity with the full Lévy noise, we'll use a truncation of the noise. Okay, so this we are able to define because the noise is truncated, so it doesn't have problems to define the integrals. And then we will let the truncation go to 0. Okay, because we will truncate the small part of the noise. Okay, and what we showed is that, okay, so the way we truncate the noise is in a clever way, so that you have martingale, and you can use martingale convergence to show that the limit exists, and then you just need to show that it's non-degenerate. Okay, so that's the scheme of the proof. And okay, so let me
Quentin,
yeah.
Sorry, I resisted asking this, but
Do not resist.
I have still some problem to understand first and the integral with from 0 to t, but you have some t1 till tk.
Yeah, it's a multiple integral. It's an integral over t1, integral over t2, integral over t3, integral over tk.
Okay.
And the second one is also a multiple integral.
And integral and all. What's the interval? Each one. What's the interval of integral for each one? All are integrals over R.
All okay. So the t's are integration between 0 and t, but
okay.
You want to order them. Okay. So you can see that as somehow integrals within one another. If you fix, for instance, if you fix t1 up to tk minus 1, you integrate tk between tk minus 1 and t. And then you integrate tk minus 1 between tk minus 2 and tk.
Okay.
Okay, so a way to write that is you put the integral over all t1 tk between 0 and t, and you put the indicator that t1 is smaller than t2, smaller than tk.
I see. I see.
Okay, so maybe yeah, maybe yes.
No, it's clear now. Thank you.
Okay. Yeah, and I didn't explain what the delta ti is because yeah, it's I think it's transparent. It means ti minus 1.
Okay. Yes.
Okay, so what you have to think about is you integrate over k time space point. Okay, I said time before because the t's are before, but okay, so you have k time space point, and you integrate the heat kernel to go from one point to the next. Okay, so that's the probability, roughly the probability that the Brownian motion goes through all these points.
I see.
And you collect the noise at these points. So yeah, that's the analogous of the directed polymer model.
Thank you.
And you sum over all possible points. Okay, so okay, and okay, so the difficulty is that if you don't truncate the noise, what you'll have is that in some places you have some kind of accumulations of small noise. Okay, so the idea is that you have an accumulations of a lot of random variables, and it's possible that your Brownian motion will just collect a lot of them, which will make the integral explode, roughly. Okay, so let me just, okay, I will conclude by saying how we truncate the noise, and maybe how do you construct the Lévy noise, because I think it's interesting, and it's a good thing to have seen. Okay, so how do you construct a Lévy space-time white noise? So the idea is that you start from a Poisson point process. Okay, so you have points in R times RD times 0 plus infinity. So you have points, this is the time coordinate, this is the space coordinate. Okay, so this tells you where you put some mass. And so this is the mass coordinate, or the weight coordinate. Okay, so you put intensity, Lebesgue in time and space, and you put a mass with a measure, which I call lambda. And for instance, if you put lambda Dirac mass, it means that all the points that you place have mass 1. If you put lambda having this formula, it means that you put a mass which has a heavy tail, which has nice scaling property, and this will give you an alpha stable Lévy white noise. Okay, so the idea is that the noise is you put a mass z at position tx. Okay, so you have points of your Poisson point process, tx z, and you put a mass z at position tx, and this gives you something which is not centered, so you need to center it. Okay, and all the problem is in how do you center it. Okay, so how do you center it? Well, the idea is, okay, you define an approximation of your noise by saying I keep only the weight on the mass that are larger than A. And here I can center the noise. Okay, I center by the mean mass of points larger than A. Okay, so that's a way of constructing okay, that's our truncated noise. And then when you let A go to 0, meaning that you include more and more of the small part of the noise, what you'll see is that this constant will go to infinity. Okay, so the idea is that you have some kind of dust or small noise in your Poisson point process, and the more you include this small dust, the more the centering has to explode to compensate this small dust. Okay, so Xi, the Lévy white noise, you can think about that as the limit of this Xi. It's the limit of this Xi in the correct spaces of distribution. Okay, I won't go into that detail. Okay, and so here you have a Lévy noise, and okay, so that's our main result, is to say that if you construct the partition function with the Lévy noise Xi A, it will converge to some thing non-degenerate under some condition on the measure that you've put. Okay, and if I put the measure which is with heavy tail, you recover exactly the result I gave before, meaning that the partition function will converge to a non-trivial random variable if alpha is strictly smaller than 1 plus 2 over d, and converge to 0 if alpha is large. Okay, so this shows that you cannot hope to construct a solution of the stochastic heat equation if your noise is alpha stable with alpha larger than 1 plus 2 over d. Okay, and I think I will stop here. Thank you.
So thank you very much. Thank you very much, Quentin, for the talk. And I would say that if there are other questions, this is a good time.
Hi, Quentin. Can I ask you a question?
Yeah, sure.
Good to see you.
Yeah, good to see you too.
So you say that if you do the truncation to psi with a parameter a, and then now your truncated partition function is a martingale. So what is the filtration for this martingale?
Okay, so the filtration is the points of your Poisson point process that are larger than a.
Okay, so so you are considering dimension 1, right? No.
No, any dimension. So dimension d is for the space coordinate, and it's always RD.
Okay.
And the filtration is only on the mass. It's only on the weight.
Okay. So the filtration is on the disorder.
Yes, exactly.
Okay. And I have another question is that I remember that you have another paper with Hubert that you can prove a result for all alpha less than 2, but in this case you have to assume that the disorder has mean should be alpha larger than 1. So is there a huge difference between the critical case alpha equals 1?
No. It's we did everything with any tail. It's just that it was simpler to present here because if I want something centered, I need to assume that it has a mean, and it corresponds to having alpha larger than 1. So if alpha is strictly smaller than 1, you actually don't need to subtract this Lebesgue part, and the truncation is correct as it is. And if you're considering the case alpha equals 1, well, you have to, somehow you have to truncate both the small noise and the large noise.
Okay. Thank you.
Yeah, probably.
Okay, so I see that that there is a raised hand from Jacques Printemps. So please, if you have a question. Okay. So you can write the question in the chat, and maybe I can read it. Okay, so the question is there a nonlinear version of this kind of results? I mean, with nonlinear stochastic heat equation?
Yeah, actually, yeah, it's a good question. There are some results. Here it's true that we were looking at only a linear stochastic heat equation, and it's because the connection with the directed polymer model is more direct, and so we have a different interpretation for the solutions of the stochastic heat equation as partition functions of the directed polymer. But I know there are some results. Carsten Chong has been working on the stochastic heat equation, and there are some kind of iterative schemes to be able to define the solutions for the stochastic heat equation. If you take the non-linearity to be Lipschitz, I think it works more or less the same. And we discussed with the Carsten Chong and Hubert about dealing with this kind of stuff, and okay, so we've developed some ideas, and I believe that some of them could adapt to the nonlinear stochastic heat equation, but actually a big part of them do not adapt that easily. So we've tried a little bit, but we didn't manage. Okay, so yeah, if you're interested in this type of questions, I think go on the website of Carsten Chong, and he has a lot of papers on the stochastic heat equation. Okay, stochastic Berger. I don't know about the stochastic Berger equation with Lévy noise. I'm sure that people have been looking at that, but it's not clear to me how one would do. Okay, a natural thing would okay. One thing that we tried also is okay. So this is the definition of our solution of the stochastic heat equation, and if you take the log of this, this is the KPZ equation, and we tried actually to show that the log of this is well defined, but it was not. Okay, we know that the log of this is well defined. But to show that it satisfies the KPZ equation is not easy, because we have to estimate some moments of the log of z, and this seemed quite hard to us, at least. Maybe some people can do that.
Okay, so maybe I have some question. So in this model, there is this space-time in which you have this word line that visits these kind of discrete points,
yeah,
that d times n.
Yeah.
And then you have this assumption about local disorder. So at each point in this space-time, there are these IID random variables.
Yes.
So I was wondering whether these kind of results could be extended to the case of some correlated noise decaying like sufficiently fast, like exponentially in the space-time distance. I mean, do you expect this framework to extend in this case? And if yes, I mean, in which case? Yeah.
Okay, so yeah, I think that if you have exponential decay of correlation, it would be more difficult, but it would be the same. Okay, so in the end, you'll still have as a scaling limit of the discrete noise, you would still have white noise. Mm-hmm. Another thing that has been done is if you have correlation in space, but you're white in time. Mm-hmm. And this changes the condition for the beta critical to be equal to 0. Okay, so people have been looking at how does this change, and constructing the solution of the stochastic heat equation with correlated noise in space. And I've been trying to look at correlation in time, and it seems really difficult. I don't know how to do that. Long-range correlations in time, it's an open problem.
Okay, thanks. So this was the first one, and the second is, I mean, these kind of results are related to the model in which space is ZD.
Yes.
So you have this nice regular graph,
Yes.
and random walk on regular graphs. So I was wondering, I mean, what happens if one consider like other graphs?
Yeah. Okay, so as long as you have some good control on the random walk and the transition kernel of the random walk, I think everything is the same. For instance, runway, consider the case where you don't look at the simple random walk, but a random walk that has long jumps.
Mm-hmm.
And you can do also things in that setting. And if you're starting to look at weird graphs, it gets complicated, and people have been studying that. There's a recent work by Clément Cosco and Ofer Zaitouni, who show that on a graph, the conjecture I stated earlier, the fact that the critical point for the free energy and for the partition function are the same. They showed that there is a graph on which it's not true.
Okay, so they provide a counterexample.
Yes.
I see. Mm-hmm.
So yeah, it's you can have some pathological effects of the graph.
I see. Okay, thanks. So are there other questions? Okay, so if not, I suggest to thank again our speaker, and yeah, so I will just comment that this will be the last talk for this year series, and we are scheduling to get back in time starting in autumn. So you can keep updated with our social media and website, and hopefully next year we will be able to give another sequence of talks in the spirit of what we've done also this year. So thank you again, and have a nice afternoon.
Have a nice day.
Have a nice day.
Thank you, Quentin. See you.
Thank you, Sophie. See you.
Thanks, Quentin. See you.
See you, Ron.